In today's video, we're going to wrap up Chapter 5. So this is part 3 of 3, and so far we've talked about the foundations of instrumental conditioning, and we're moving through the key components, the basic players involved in instrumental conditioning. So our moving parts, and we started with the instrumental response itself, and that was how we finished off the last video, and so today we're going to start off talking about the outcome of our response. Basically, what is our reinforcer in this given situation? And I did mention in the last video that the textbook focuses mostly on reinforcement at this point. We will talk about punishment later on, but just for the sake of ease, we're going to stick to the reinforcement side of things, just because that's what the textbook does, and then punishment has its own special considerations, which we'll get into in later chapters that we cover in this class. So this isn't exclusive to reinforcement, it's just easiest to talk about using reinforcement, and then we'll expand later on. And then once we've covered the outcome of response, or our reinforcer, then we're going to talk about the relationship between the response that's made and the reinforcer that's given. So we've talked about, or we will have talked about, both individual components, and then we'll talk about how they relate to one another. All right. So enough setup, let's actually talk about our instrumental reinforcer. What factors are we going to discuss? So the first we want to discuss is the quality and the quantity of our reinforcer. So how effective a certain stimulus is as a reinforcer will depend on both the quality and quantity of that stimulus available. If you're trying to motivate a young child, a bag of M&Ms might be a lot more motivating than a single M&M because of the quantity of M&Ms. Or maybe they're not a chocolate person. Maybe that child prefers sour candies, and so they want Sour Patch Kids instead. So if you gave them Sour Patch Kids, that might be a better reinforcer than using M&Ms because of the quality of the thing that you're using. We're also going to talk about previous experience with other reinforcers, so how we can relate the current reinforcer to other experiences with reinforcers. And we'll discuss each of these in more depth on the following slides. Rather than talking anecdotally about children wanting more and better things as reinforcers, and that would be more motivating, let's actually look at some data that supports this idea that a better quality reinforcer is going to cause more of a behavior than a lower quality of a reinforcer, and the idea that a larger quantity of a reinforcer might be more motivating than a lesser quality of that reinforcer. Now, this experiment here was done by Hutt in 1954, so this is quite an old one. And this isn't actually in your textbook. This is a different example, just to switch things up a little bit. The textbook uses its own examples, but it's all illustrating the same idea. So let's talk about a new one. New old experiment. But in this experiment, basically a pretty simple operant setup where we have a bunch of different groups of rats that were being reinforced for button pressing or lever pressing, which we'd call it rats, where whenever they'd press the lever, or whenever they'd press the lever a certain number of times, they would end up getting some kind of water reinforcement. So for a setup, we would probably have rats whose only way of getting water was to press the bar, just to ensure that they would actually press the bar and want water. So we'd use sort of mild deprivation just for the experimental procedure. And we would have 9 different groups that varied along 2 different dimensions. So the first dimension would be the quality of the water reinforcer that they were being given. So at the top of our graph here, we have 3 different types of water that they could be given. One would be acidic water, where they would add an acid to the water just to make it basically bitter and not as tasty. So that would actually reduce the quality of the water. Our next group would just be plain old water. And then our last group would actually be increased quality water, where they would add sucrose or sugar to the water to make it sweet. So we have this variation in quality of the type of water that they were receiving. So low quality, normal quality, or high quality water. We would then also have variance in the dimension of how much water they got. So the quantity of water. And we can see that across the bottom of the graph here, where we would have a small, medium, or large amount of water delivered as a reinforcer when they pressed the lever. And so the experiment was just looking at how many lever press responses were the rats making in a given amount of time. So that's our responses per minute on this axis here. And so we can see this really interesting, nice, clean illustration that each of these 9 groups show that as we increase the quantity, as we go from small to medium to large, we tend to see that increasing trend, regardless of what kind of water they had. So even if we look at the acidic water, we go from sort of not a lot to a little bit more to a little bit more. If we look at our sweet water, we go from this amount to more again. So from small to medium to large, increased in quantity meant increase in behavioral response. And then if we look within any one of these conditions, so if we look at all of the rats that received only a small amount of that reinforcer, we see that if our normal water is our standard, sort of our baseline consideration, then the rats that got acidic water were that decrease in quality, and the sweet water is that increase in quality, and we see more lever pressing behavior for the increased quality and less lever pressing behavior for the decreased quality. So the same idea that as quality increases, so too does the behavioral response to it. And so we can see this nice clean variation along both dimensions of quality and quantity within one experiment. So a really nice clean experiment and one graph to show what we've been talking about. Now, the next thing that we want to consider is, well, what if these groups weren't independent? What if we used the same rats and some of them would start off getting a small amount of water and then they'd get a medium amount and then maybe later on they'd get a large amount? What if they had prior experience? How would that change their behavior? And so that's the second thing we want to consider about our instrumental reinforcers. What's the previous experience that these organisms have with other reinforcers? If they're experiencing a shift in quality or quantity, how does that change their behavioral responses? And so this kind of gets into the idea of expectation. Not all researchers are going to use the term expectation, especially behaviorists don't like that idea of like anticipation or knowing that something is coming, but it is a good descriptor for what we're talking about. Now, this should make you think a little bit, at least, about our Rescorla-Wagner model, which we talked about back in Chapter 4, where if there's a deviation from your expectation, we might see more or less, for Rescorla-Wagner, more or less learning. For what we're looking at here, we might expect more or less responding based on that learning that's happening, that's shaped by our expectations. So if you have something that is very surprising, if it's a lot larger than what you expected, then you might see excitatory conditioning. You might see more responding. But if it's smaller than you expected, if there's less than what you were anticipating, then you're going to see inhibitory conditioning or a reduction in responding. So our previous experience allows us to build up that anticipation and is going to affect how exciting a particular exposure is going to be, and it's going to decide which direction our behavior changes based on what we're learning. So let's look at another experiment that's going to involve manipulating our reinforcer, and this time we're going to be doing these manipulations within subjects. So each subject is going to have some kind of prior experience with that reinforcer, and we want to see how their behavior changes based on their previous experience and what they're experiencing now. So in this situation, we're going to be looking at rats yet again, but this time we're going to use a discrete trial procedure rather than our free operant that you would usually see with an operant box with something like a lever press. But here we have one of their loosely called mazes, basically just a straight hallway where you start the rat in a box at the beginning in their starting position, and then you open up this doorway here to allow them the ability to run down the maze to the end where they would receive their reinforcer. So it's a straight runway. They go from the start to the finish, and what we measure is how long it takes them to go from the start to the finish. In most of these experiments, there's usually a delay period at the beginning where they place the participant in the box here at the start and they wait. They don't allow them to just immediately run down the maze, because if you do that, you tend to find that the rats just run at full speed all the way through, no matter what. But if you force them to wait for just a moment to acclimatize to being in that box and then allow them to run, then we do start seeing that variation in speed. All right, so that's the basic setup here. We're going to have 4 different training groups. The first is initially taught with a small reward and then is given a large reward. So what we have here right now is, say, 10 pieces of cheese. That would be a large reward. Maybe when they were first trained, they would only have 1 piece of cheese. And so once they'd been trained up with 1 piece, they would switch and suddenly be given more. They'd be given 10 instead, so they went from small to large. The other group would go the opposite way. They would start large and then go small. So they'd start with 10 pieces of cheese, and then they'd be switched over to only getting 1. And then we'd have our control groups, where you start large and stay large, and another group where you start small and you stay small. And then we measure that running speed from the beginning to the end and how that speed changes based on what they were used to originally and what they were experiencing at the end. So let's see what their data looked like. So on this graph here, we have at the bottom basically our time component. So our pre-training and then our subsequent training procedures after they had been trained on the initial stage. So set 1, 2, 3, and 4 for blocks of trials. So just over the course of time. And then, as I said, we're measuring our running speed, and then we can look at our different kinds of groups. So our small control group, our large to large control group, and then our switching groups, which we could consider experimental groups, where they start small and then get large, or start large and then get small. And so at the very, very beginning, the important thing to note is that during this pre-training stage, when they were first being taught, our 2 circles, which are our 2 large start groups, were a little bit faster than the 2 sort of square and then the triangle groups at the bottom here, which are the ones that start small. And that's just saying that when you are used to a larger reward, you might be a little bit more motivated to move quickly, but it's not a huge difference. They're all fairly close together. And especially where we're interested in the difference and how those change over time, these are actually fairly close together. So we're starting on an almost equal footing. But if we look at our small to large group, so our triangles, these go from, at the beginning, pretty slow running speed. And then we see this dramatic climb where by the time they've gone through the first and even into the second block of trials, they're responding much, much faster. So they're running from the beginning to the end of the maze so much faster because now they're getting something that's bigger than they expected. So we're seeing more responding because this was exciting in the positive direction. They're getting more than what they were expecting, and that's really good. And so we can call this a positive contrast, where we now have elevated responding because their prior experience with a less attractive outcome makes this current, more attractive outcome that much better. So 10 pieces of cheese looks really, really good when you're used to only getting 1. And then if we look at the opposite with our large start and then small finish group, we see the opposite direction, where they started at almost the exact same point, but we see a drop off in their behavior here because they were used to getting 10 pieces and now they're only getting 1. So that's a negative contrast where we see a depressed or decreased responding because the small reward looks bad based on their being used to a much larger reward. And then if we wanted to look at our control groups, our circles here, the large to large stays pretty much flat. Our squares go up and down and then back again. So this is kind of, if you averaged it all together, pretty flat as well. We only see that continued trend for the ones that have that change, the small to large and then the large to small. So we have two different kinds of behavioral contrasts that we've seen here, where we can have a positive or a negative change, and it all depends on our prior experience and what we're receiving now. All right. Now that we've talked about the instrumental response on its own and the outcome of the response on its own, let's talk about the relationship between the two. So, how does our response relate to the outcome? Now, it makes sense that this relationship should be really important, because the hallmark of instrumental behavior is that it produces and is controlled by the consequences of your responding. And if we think about it logically, if something has a strong relationship, if doing a particular response always gets you a particular reinforcer and it has a strong relationship, then, that would be a good way to learn that relationship. So if you think of a vending machine and you put money in and you get the thing that you want out of it, then you're going to be more likely to put money into that vending machine to get the thing that you want in the future. We can weaken that relationship by maybe reducing the reliability of that relationship. So if the response of putting your money in the vending machine only sometimes gets you the reinforcer, only sometimes you get the item that you want, then maybe you're not going to put money in that machine as often. You're a lot more likely to trust and use a reliable vending machine than an unreliable one. So if we're kind of quantifying them, that would be the probability of getting the response that you want. And we'll talk much, much more about that in the next chapter when we start getting into our schedules of reinforcement. But just as a quick reminder from 282 and back in 104, we can have either continuous reinforcement where every behavior gets that reinforcement, so you have a very reliable vending machine, or you can have something where it's intermittently reinforced, where not every time you use the vending machine you get what you want, but you get it sometimes. And that relationship between when you do the behavior and when you do or don't get that reinforcer, that can affect how strong that relationship is, and it can affect what we're learning when we're going through this operant conditioning procedure. So what kind of relationships are we going to talk about? The two big ones are temporal relationships, where are they close together in time? We can also call this temporal contiguity, which is basically saying that when you do the response, the outcome follows shortly thereafter. And we've already mentioned a couple of times during this class that if there's a long delay between when you do the response and when you get your reinforcer, it can become harder to associate those two actions. And then it can be harder to learn that association because of the delay. So the time between our response and outcome absolutely matters. The causal relation between the response and the outcome, or as we can call it, the response reinforcer contingency, can also strongly affect this relationship. And just very briefly, this is the extent to which the response is necessary and sufficient for the occurrence of the reinforcer. Basically, is that action a necessary element in getting the outcome that you want, and does that outcome only happen when that particular response is made? And the more certain we are that action A causes outcome B, then the more we're going to learn about A and B occurring together. or at least being related to one another. And as always, I'll be talking more in depth about each of these on the next slides. I just want to give you a brief overview of where we're going. All right, so starting with temporal contiguity, the two events happening close together in time. And as I've said, immediate reinforcement is preferred. Having the outcome immediately be followed by that consequence is the best way to learn an association between that response and the outcome. And this idea goes back all the way to Aristotle's primary laws of association. So this is not a new idea. And it has been constantly shown to be the case where faster reinforcement is usually better for learning. Originally, the common rule was that any kind of delay more than half a second can hinder performance or hinder learning. So you would want to have very, very immediate responding, very immediate consequences or reinforcers presented, because you wanted to make sure that the animal knew that the response was immediately tied to that consequence. But more recent research has suggested that you can actually use delays as long as 30 seconds without significantly damaging that association. I will state that up to 30 seconds is sort of with a little asterisk at the end saying under ideal conditions. When in doubt, it is still going to be better to have as short of a delay as possible, but you want to have stuff's going to vary based on what kind of experimental setup you have and which organisms you're using. The other side of that caveat is that in some species, even a delay of 0.5 seconds can be hindering. So some species, it needs to be even more immediate than that, again, under certain conditions. So we'll stick with the broad rule that sooner is better, but it doesn't have to be as immediate as we once thought in all situations. And of course, let's look at some data to cover this. So this diagram is for a very simple experiment, pretty identical to stuff we've talked about previously. This would just be a standard free operant procedure where we would have a rat in an operant box, and when they would make a lever pressing response, then they would be reinforced with food at some point thereafter. And so because we care about the effects of delayed reinforcement here, we would have rats who would experience delays of very small amounts of delay, so almost immediate reinforcement, up to very, very long delays. And so this experiment looked at the difference between about 0 delay all the way up to 64 seconds or more, and saw how quickly or how much lever pressing we saw in rats that were reinforced with that much of a delay. And so the idea here being that if the rats are learning that pressing the lever leads to food being delivered, they would press the lever more. So higher rates of lever pressing means that they've learned more, which means that they have learned this association between lever pressing and getting food. And we see, as we would predict, that we see more lever pressing when there is a very short delay. So between 2 to 4 seconds, we see the highest rates of learning. So shorter here is better. We see lots of lever pressing there. However, still some lever pressing. There was still some learning, even in the range of, say, 10 to 20 to even 30-second delays. There is still some learning going on there because they're still pressing the lever more than not at all. However, once we get out past a 60-second delay, there are really low rates of responding, and after 64 seconds, they pretty much saw 0 responding in all of their rats. So anything longer than 64 seconds of a delay, you don't see much learning at all. So this is our general rule, where shorter is better. You can still see some learning in moderate amounts of delay, but not as good as when they're short delays, and then really long delays have pretty much no learning. But why? Why do we see this pattern? Why are organisms so sensitive to delay? And the basic idea is that when there's a delay, it's actually really hard to determine which behavior that you've performed was the cause of you getting that reinforcer. basically you find it hard to decide which action you should credit for getting that reinforcer. So if we look at this simplified diagram here, we have two instances of reinforcement. So a rat got food at this time period and got food again at this time period. And maybe they're getting food after 5 seconds when they pressed a lever, and that's response number 1. But there are other things in the cage. Maybe there are other levers. Maybe there are buttons. Maybe there's a water bottle. And they're doing things like drinking from their water bottle. That's R2. R3 is that they press a different lever. And R4 is that they press a button. And if there's a delay between the behavior that they're doing and when they get that reinforcer, there might be other tasks in between that could be linked with getting that outcome. So how do we overcome this issue of not knowing which particular behavior was responsible? We can use something like conditioned reinforcers. This would be something like clicker training. So if you have ever seen clicker training done in dogs, I can't remember if we've shown a video of this before, but probably, where you associate the sound of a clicker with your dog getting a treat, and over time they associate that clicking sound with getting a treat reward, and so they start to associate that sound with something good. That click sound is now a conditioned reinforcer. We have conditioned them to associate that sound with good feelings, so when you make that click sound, they feel good. So if we have all of these different behaviors and we're not going to give the reinforcer for a little while, right after they do the response that we want them to do, right after they push the right lever, we could use a clicker, make that sound, and they would get that conditioned reinforcer immediately to let them know that they did the right thing. And then later on, afterwards, they could get the proper food reinforcer, but they know that because they have that good feeling sound right after this behavior, that's probably the behavior that was important. And this is very similar to the idea of marking, but you can just use a sound or some other kind of stimulus that marks the response that they just did as special. So you can play a sound or have the light change or something like that to make it more memorable so that it is easily distinguishable from the other activities that the organism has done. And the difference here between marking and a conditioned reinforcer is that the conditioned reinforcer has been conditioned to be a reinforcer, whereas marking is going to be what is still a neutral stimulus, whose only purpose there is to make sure that you note the behavior that you just did. It doesn't necessarily tell you that you should feel good about it, it just tells you that that behavior is special somehow. And as per usual, we can look at some data that actually illustrates these points. So here we have, again, lever pressing rats in an operant box, so a free operant procedure, and we're going to look at a couple of different groups. So we're going to have a group that has no signal at all, so just a standard rats press the lever and 30 seconds later they get food delivered. We're going to have a marking group where when the rats actually press the lever, then a group would be presented immediately after the correct behavior, the lever pressing, was done, and then they would still be receiving their reinforcement 30 seconds later, but that light turning on marks the fact that pressing that lever was significant or important. And then we can have a blocking group, which would be that they press the lever, and then right before the food reinforcer was delivered, the light would turn on. So because that light happened right before they received food, and the light is much closer to the delivery of the food than the lever pressing was, it tends to interfere with them associating the lever pressing with actually getting food. Instead, they associate the food with the light, so that's why it's blocking. But if we look at the graph here, we have reinforcers per hour, which is basically how often are they getting food in that hour period. And then at the bottom, we have our time increment, which is basically blocks of 2 sessions, so however many sessions we're looking at. And if we look at our blocking group of as expected, we see very few reinforcers received because they didn't really learn that pressing the lever was necessary for them to get that food reinforcement. So they didn't think to push the lever because they just associated the light with the food and they didn't push the lever. If we look at then our no signal group, which are these open circles, this is what we would expect. With a 30-second delay, it takes them a while to learn that pressing the lever gets them food, but they do figure it out, and we do see a slow increase in how much lever pressing they're doing over time. What's really cool is that the simple difference of just having a light that they know nothing about turn on immediately after pressing that lever, we see a dramatic rise in lever pressing responses, and they get so much more food in this group just by that one simple change. So marking can be a really effective way of marking or showing that a particular response was correct or important, and it makes that association that much easier, which is really cool. All right, so that's our time relationship between our response and the reinforcer. Let's talk about that causal relationship, or our response reinforcer contingency. Now, in most of the studies that we've looked at so far, when we're looking at delay of reinforcer, those are almost always perfect contingency setups, where every lever press leads to a food reward at some point. And we still saw disrupted learning when we delayed for longer and longer periods of time. So originally, researchers thought that the time component was the only important part of this relationship. And so the idea of a causal relationship, or whether there is a 1-to-1 ratio between the response and the contingency occurring, wasn't as important and wasn't really necessary for this learning to occur because the time component was so much more important. Even Skinner thought that only that temporal contiguity was needed in order for the organisms to learn an association. And indeed, this idea that time component was the only important part of this relationship led to a very famous experiment that most behaviorists will talk about, most behavioral researchers will talk about, and that's Skinner's superstition experiment. So if you haven't heard about this experiment, then we're going to talk about it now. If you've already heard about it, we'll try and keep it fairly brief. But this, as I said, it's a very famous experiment, so you've probably at least heard it in mentioning. So this experiment was set up to try and pick apart whether time alone was sufficient for an association to form, or if there had to be some kind of response reinforcer contingency involved. And so to do this, they had pigeons in an operant box where reinforcement was delivered every 12 seconds, regardless of what behavior they were doing. So instead of having the pigeons have to do a particular behavior in order to get food, every 12 seconds, food would be delivered no matter what the pigeon was doing. So the pigeons could be pecking a key, or they could just be walking around, or they could be drinking water. They could be doing absolutely anything. And so Skinner reported that pigeons were developing quote-unquote operant responses independent of any kind of contingency or any evidence of causality, where they would be doing whatever behavior they happened to be doing the first time they got the food reward more often, and then they would start doing those behaviors all the time, sort of falsely assuming that doing that behavior was required to get food. So if you had a pigeon that was drinking water when food was first delivered, they would then drink water more often in an attempt to get more food. But because they would then be drinking more water, they'd be more likely to be doing that drinking behavior when food was delivered again 12 seconds later, which they argued would be enough to then reinforce that behavior because they're getting food after having drank water. So then they would drink more water and then be more likely to be drinking when they get food the next time, and so on. So you get this runaway idea where temporal contiguity is all that's important for this association to develop. There isn't any need for a causal relation between the behavior and the outcome, because them occurring close together in time was sufficient for that association to be learned. And if you've ever looked at this experiment, there are a ton of cool and weird different behaviors or superstitions that some of the pigeons developed. Just a couple of the highlights include birds that thought they had to turn either clockwise or counterclockwise in order to receive food. One of them repeatedly thrust his head into one of the upper corners of the cage, basically trying to bob his head in a particular position, or tossing their head upward as though they were lifting a bar, even though there was no bar. So when Skinner published this, it was saying that look at all of these varied responses that can develop simply from superstition. So clearly a causal relationship isn't necessary for this kind of association to occur. And of course, this was a very hot topic for a while, and eventually somebody wanted to try and replicate it. They wanted to figure out what exactly is going on here. So in the 70s, Stattleton and Simmelhag decided to reinterpret and try and replicate Skinner's superstition experiment. And they wanted to do sort of the same thing, but more extensively. They wanted to be more precise with their observations. They wanted to measure the frequency of many, many more different behaviors. And they wanted specifically to look at when during the interval between successive feedings each type of behavior occurred. Basically, they wanted to turn it into a proper experiment instead of just a observation and kind of anecdotal report that Skinner had originally proposed. And so some of the things that they were looking at was their interaction with the magazine wall where the food was, pecking a key, pecking the floor, turning in a circle, flapping their wings, so on and so forth. So they had lists and lists of different behaviors that they recorded, and not only did they record the frequency of those behaviors, they also recorded when they occurred in time across all of the trials that were observed repeatedly. So these are kind of weird diagrams over here, but these are showing, so for individual number 31, so this would be pigeon 31, which just means that it probably had a band on its leg with the number 31 on it, and we can look at the occurrence of different kinds of behaviors across different time periods. And so we can read this as the occurrence of a certain behavior, so the probability of a behavior occurring. Higher means the bird is doing that behavior more. And then across the bottom here is just our time interval. And so we have here response 1, which is basically orienting towards the magazine wall. Response number 7 would be pecking directed at that magazine wall. Response 11, which it might be hidden underneath here maybe, or maybe it's one of the ones down here, would be putting their head into the magazine. And the cool part here is that they see pretty predictable patterns of these behaviors occurring. And the two graphs here I didn't think to mention, whether it was a fixed interval or a variable interval. So the responding was still independent of whatever the pigeon was doing, but it would happen either at a fixed interval, say every 12 seconds, or with a variable interval, which would be every 12 seconds plus or minus a certain amount of variability. And we see pretty similar patterns here, regardless of whether it was at fixed or variable intervals. These behaviors seem to happen either early or late in that time period. And so things like pecking at the floor or turning around would be a lot more likely to happen at the beginning of the interval when the birds pretty much know that food isn't coming for quite a while. They have a whole 10 or 12 seconds left before they could get food, so they're going to turn in a circle, or they're going to peck at the floor, or they're going to move around in the cage. So that's what those early peaks are just random behaviors of them killing time. And then towards the end, we get those behaviors like turning towards the magazine wall. And the magazine is where the food is delivered from. They would start pecking at the magazine wall, or even put their head into the magazine as they get closer and closer to the time in which they would be getting food. So that kind of makes sense. They would do food-related behaviors closer to when food is being delivered. This isn't superstitious at all. This is just the birds preparing to go and get the food that they know is coming at some point in the near future. And so the results here show that there really wasn't any kind of accidental reinforcement effect. There were no superstitious behaviors. The behaviors that were occurring tended to make sense based on when during the trial they occurred. Early on behaviors tended to be other random things, but as we get closer to food delivery, we'd see behaviors related to food delivery. So the responses that occurred coincidentally with food delivery didn't end up occurring Basically, the things that the pigeons happened to be doing towards the end of the trial when food was delivered weren't increasing in frequency because they happened to be reinforced. They were just behaviors that were related to the birds getting food. And over multiple trials, the birds would have their head in the feeder the same amount of time because they knew that food was coming. But it wasn't being strongly reinforced. They didn't sort of learn an association between pecking at the magazine wall and getting food. They were just there because they were waiting for the food to be delivered in the near future. So this ended up kind of refuting that idea of superstitious behaviors developing. And instead, what we're seeing is that we have terminal responses, things that are produced near the end of the interval. So going over to be near the feeder. And then we'd also have interim responses, which are the things that they did when they knew they had time before food was delivered. So things that are produced immediately after food delivery, before the next delivery is imminent. And if we wanted to, we could tie this back into that behavior systems view that we've mentioned quite a few times now throughout this chapter, where we might have a focal search or a general search. So a general search might be at the beginning of the trial in this interim response period, where they don't know that food is coming immediately. Maybe they have some time. They just got food, so now they have time, and they can start looking around. They can do other behaviors like pecking in the dirt or walking around. But as we get closer to the time that food will be delivered, we enter into that focal search period, where they're going to be in the area where food is delivered, and they're going to be up near where the food comes out of the magazine. Now, we're not quite sure why Skinner's experiment failed to observe such predictable behavior sets. Maybe Skinner wasn't as focused on when during the trial different behaviors happened, and in some birds he saw the terminal responses, and in other birds he would see interim responses. It's not quite clear. What we do know is that this study and other studies that have sought to replicate Skinner's superstition study haven't actually been able to support those conclusions. So, as cool as it was to see those superstitions, and as neat as it might have been, it doesn't seem to actually be a real thing. But if you do want to spend some time, you can Google Skinner's superstition experiment, and there are some really neat videos of him showing off some of those potentially superstitious behaviors. But after that unique detour, where people originally thought that this response reinforcer contingency wasn't essential, now we know that it is actually important in forming a relationship between both the response and that reinforcer. And so if we have a strong contingency between the response and reinforcer, we know that the response controls the delivery of that reinforcer. A rat is a lot more likely to learn about the relationship between lever pressing being related to food if every time they press the lever, they then get food, and if the only way to get food is to press the lever. Basically, if we set up a very strong contingency where the two are closely tied to one another. And what we learn about that association is going to affect behavior. So our behavior ends up being very sensitive to these response reinforcer relations. And there are lots and lots of different studies that look at the effect of control over reinforcers, where your behavior has some kind of influence over what kind of reinforcer or outcome you experience. But some of the very special cases of looking at this kind of control end up looking at control over aversive stimuli. So, for example, negative reinforcement. So what we're going to talk about next are actually some special case scenarios, which you might have heard of in the past, but we're going to talk about again here. So one of the key ways of talking about the controllability of a particular kind of reinforcer is to look at the learned helplessness effect, or LHE. Now, studies that were looking at learned helplessness were basically seeing what happens if you remove that control component. What if that outcome is going to happen no matter what? Now, this idea of learned helplessness was mostly studied kind of related to escape and avoidance learning. So we've already talked about escape conditioning and avoidance conditioning, where escape conditioning would be some kind of aversive stimulus is happening, and you can do a behavior to get away from it. So maybe a rat is in a box and there's a very loud sound playing, but if they push a lever, then the sound will turn off. That would be an escape behavior. Whereas avoidance behaviors are even cooler because they learn that an aversive stimulus is coming up and that they can do some kind of behavior, like pushing a lever, in order to avoid that aversive stimulus ever happening. So a light turns on in the cage and the rat knows that a loud sound is coming, but they push a lever and that makes sure that that sound won't happen. So that is closely related to this learned helplessness idea, because learned helplessness took it one step further and said, what happens if we remove the ability to escape or avoid that aversive stimulus? What if we remove that control component? So if you have a rat where there's a loud sound happening, or they know a loud sound is coming, but they can't avoid it or they can't escape it, what then happens to their behavior? And the answer is the learned helplessness effect. So this describes the findings that there is an interference with the learning of new instrumental responses as a result of exposure to inescapable and unavoidable aversive stimuli. So in that idea of a rat having a light that comes on that lets them know that a loud aversive stimulus will be presented in the future, when they can use avoidance behavior, when they can press a lever to stop that aversive stimulus from happening, then they're going to learn that that light is warning them that something bad is coming, the very loud sound. But what the learned helplessness effect says is that if we take away that aspect of control, even though the light still reliably predicts the arrival of that loud aversive sound, they're not going to learn the relationship between the light and the aversive stimulus because it doesn't matter. It doesn't help them any way, shape, or form. So let's look at an experiment that was looking at this. So this is the standard setup to study both escape conditioning and avoidance conditioning, but also our learned helplessness. So we're going to call this the triadic design, and there's going to be an extra step to let us study learned helplessness here, but we are going to have standard escape avoidance training just like we've talked about previously. So step one is to have an exposure phase. Now during this phase, we're basically just establishing the fact that there are shocks that can be delivered. And so as we've said before, when we talk about aversive stimuli, these are meant to be very mild, just slightly aversive shocks. They're not meant to cause large amounts of pain or discomfort. You can do the same thing with loud noises, anything that's mildly aversive that would cause them to learn that it's something they want to avoid if possible. So this isn't intended to be startlingly painful. Just a small disclaimer there. But we have three different groups. So group E is our experimental group, and it is an escapable shock group. So in step one, They might be in the shuttle box, but they're not allowed to move freely between the sides. They'd be stuck on, say, one side or the other, where there would be a shock that occurs, but there is a behavior that this group can perform to stop that shock. So they can escape that aversive stimulus by rotating a wheel. And you can set this up where any kind of behavior can escape that, pushing a button, lever, whatever. So this group E can do something to stop the presence of that shock. Group Y is a yoked group where they're basically partnered. So individual 1 from group E is partnered with individual 1 from group Y. And whenever individual 1 in group E receives a shock, so does the individual in group Y. But nothing that the individual in group Y does is going to change the occurrence or duration of that shock. That existence of that aversive stimulus is tied solely to the behavior of the individual in group E. So these individuals have no control. They have no way to escape the shock. So we call it a yoked, inescapable shock because their behavior is irrelevant and the occurrence of those shocks is yoked or paired with an individual in another group. Our third group is a control group where these rats would be restricted to the apparatus, but they wouldn't receive any kind of shock. They're just there for the same duration that the other rats were for a control. For our second phase, we go through a normal escape avoidance conditioning phase. So, as we've discussed before, you use a standard shuttle box. This opening will be open again, and there would be some indication that a shock is coming. So usually a light will turn on, and it lets the animal know that they should move to the other side of the box to avoid that shock. Or if they're being shocked, they can escape by moving to the other side. So they can either escape or avoid depending on how much they know. So that's our conditioning phase where they are trained in a shuttle box and can move freely between both sides. And our outcome is that those who were in the original escapable shock group learn rapidly to avoid that shock. So they learn that these shocks were something that I could escape previously. So when the light comes on, I know the shock is coming, so I'm going to go to the other side of the cage and I'm going to avoid it completely. And we'll skip down to our control group, our R group, which also learned very quickly that when that light comes on, it means a shock is coming and I should move to the other side of the enclosure and avoid being shocked. But where it gets really interesting is that our yoked group that was originally trained with an inescapable shock ends up showing very slow avoidance learning. They learned early on that this shock is something that's going to happen no matter what I do, so they stop trying to avoid it. They don't learn that that light signals the shock is coming and don't think to move to the other side of the apparatus. So we can say that these animals can perceive the contingency between their behavior and the reinforcers. And animals in that yoked group learned that the shocks are independent of their behavior and are therefore inescapable and therefore unavoidable. And over here are just the data that support what we just talked about verbally. The numbers themselves aren't very important. They're just showing us that the yoked control group end up failing to escape a lot more often and take a lot longer to learn. Now, I do want to point out here that this is the learned helplessness hypothesis, and this one here is the learned helplessness effect. So the effect is talking about the pattern of responding that we observe in that triadic design, whereas the learned helplessness hypothesis is an interpretation or possible explanation for that observation. So the hypothesis is put forward to try and explain the effect, just as something you might want to keep in mind. From that research on learned helplessness, which is actually now used as one of the main models when we're studying depression in non-human animals, so a fairly important field, that has sort of blossomed off, and now there's another line of research that tries to focus on why exposure to escapable shock or escapable aversive stimuli isn't as bad as the inescapable aversive stimuli. So let's first talk about those escapable aversive stimuli. So when we have an escape behavior, there are certain responses that you can make, certain skeletal responses, actions that you can do, and those actions provide sensory feedback cues. So when there is a shock present, and an animal can make that escape response, they can do that action that will cause the end of the shock and the start of the period after the shock. And so we can have shock cessation feedback cues, basically what you're feeling as you are causing the end of the shock. And then, even more importantly, are these safety signal feedback cues. So this idea that the shock has now stopped and you're in that period where no shock is occurring. Now, these safety signal cues can act as conditioned inhibitors of fear. There's an absence of shock here, so they feel safe, they can relax. However, in our Y group, our yoked group, they don't have any ability to predict the shock, and they don't have any ability specifically to predict the end of the shock. So they don't get this feeling of safety at the termination of the shock because they don't know why it's ended and they don't know when it's going to happen again. So individuals that can escape that aversive stimulus get that period of relief afterwards because they know it has ended and it's not happening again right away. But in a group that has no control, in that learned helplessness condition, they don't get these safety cues, and so they don't get to relax. And so this tells us that learning to predict the end of the shock and then the subsequent absence of the shock is just as important as being able to, is just as important as actually escaping the shock itself. So this feeling of relief afterwards can be really important. And of course, this is very important to carry over, especially into humans, where we want to look at things like depression and escaping other aversive stimuli. So looking at things like PTSD, where people have lots of things that they would like to be able to escape, but if they have this learned helplessness, they don't get that relaxing or safety signal after the stimulus has ended. So the difference between controllable and predictable aversive stimuli versus uncontrollable and unpredictable stimuli is very, very important for things like this. And the one thing we can add from this next slide, because I already covered the first two, is that if we can somehow include an external shock cessation cue, if we present, say, a tone or a light at the end of an inescapable shock, then we can actually eliminate these learned helplessness observations. We can get rid of learned helplessness because we're giving them a signal of safety. And so that shows us that that safety signal is very, very important in this learned helplessness effect. All right, so that brings us to the end of chapter 5. So we started off with our history of instrumental conditioning, and though we only touched on some of the very high points, we can conclude that instrumental conditioning research has a very long history, and a very sort of convoluted history. We started with Thorndike, we moved on to Skinner, and then we talked about how we've gone from there into modern views. We've talked about how temporal contiguity and contingency both play a role in what we learn and how we learn it, and we can have lots of different interpretations of behavioral data, specifically looking at Skinner's superstition experiment and then the follow-ups. But as I've said early on, this is just our foundations of instrumental conditioning. The chapters that come after are going to build on this. We're going to start looking at schedules of reinforcement and other mechanisms involved in how instrumental conditioning works. So we're going to keep talking about these topics and we're going to get even more in-depth into them, but this is a pretty good background, a good foundation to get us started on the topic.